So what we've got in question 53 is we've got an object. All right, so here's my object. And there are some forces acting on this object. One force is pointing due north. So it's acting something like that. And I'll call this guy F1. And it has a magnitude of 80 newtons. Now that's not all. There is another force that has a magnitude of 60 newtons and is due west. So he's not quite so long and is pointing due west, which I'll say is that way. And so if I just note down that magnitude. Now there is yet a third force acting on this object that we don't know much about. Something we do know, however, is that this object is moving at constant velocity. And if something is moving at constant velocity, that means it's not accelerating. And that means, by Newton's first law, that the net force on that object has just got to be zero. So whatever this third force is, it has to be directed and have magnitude such that it just happens to balance out these two other forces. So just on the basis of that, then I would say, going from my diagram here, which is obviously not scaled, but just going by this, I would say that that third force is probably going to have to be out in a direction something like that. So let me call that F3. And what we want to know is, what is that vector? What's its magnitude and what's its direction? Now its magnitude is just going to be equal to its length, but what about its direction? How do you specify that? Well, how I think I'll specify it is by saying what its angle is in the southerly direction from east. So if I just draw up a right-angled triangle around this thing, then I'm going to specify the direction of this thing by specifying this angle round here. So this line here would be in the easterly direction, and this line here would be in the southerly direction, and I'm going to specify the direction of F3 by this angle here. So that may not please everybody. I'm not sure if it'll please the question or not. But once you know this angle round here, then you know pretty much everything there is to know about the direction of this object. Once you know that angle, you could find the direction of this vector as an angle from any other of the other directions, so north or west or east. So anyway, we know that the net force acting on this object is zero. That means that if we took these three vectors and added them up, we would have to get a vector that just has zero length, has nothing at all. So one way of doing that, I guess, would be to try to get a scale diagram and try to, and would be just to draw it up to scale and figure out what this vector has to be in order that these three just add up to zero. Instead of getting into drawing scale diagrams, however, I think I would like to use a, well, for me, easier method, and probably for most people, and that is to split these vectors up into perpendicular components, specifically x and y components. So let me define what I mean by x and y. By the y direction, I mean the direction of north, and by x, I mean the direction of east. So these are the positive directions. So here, according to this coordinate system, south would be the negative y direction, and west would be the negative x direction. So if I split these three vectors up into their x and y components, I then know that the sum of the x components is going to have to be zero, and the sum of the y components is also going to have to be zero, because the net force, the x component of the net force, is just equal to the sum of the x components, and the y component of the net force is going to be the sum of the y components. And since the net force is just zero, its components are also going to have to be zero as well. So the first thing I would like to do is to split these three vectors up into their x and y components. So let's say split vectors up. X and y components. So first of all, let's have a look at F1 and what is its x component. Well, F1 is just pointing in the y direction, so it doesn't really have an x component, or if it does, it's just 0. So its x component is just going to be 0. Now its y component, because F1 is just pointing straight up the y-axis, that means that the length of its y component is just going to be equal to the length of F1 itself. So this the y component of F1 is just going to be equal to the length of F1, which we know is 80 newtons. But I'll just call it F1. So this F1 without the little arrow over the top just means the length of this vector and is the same thing as F1 vector with two modulus signs around it. What about F2? Well, F2, unlike F1, is pointing in the x direction. And since it is pointing in the x direction, the length of its x component has to just be equal to the length of the vector itself. So here, that's going to just be equal to F2, which is that 60 newtons. With a slight complication in that because F2 is pointing in the negative x direction, its x component is going to have a negative sign out the front. And as for its y component, well, because it's pointing in the x direction, its y component is just going to have to be 0. I mean, because it's pointing entirely in the x direction, its y component is going to have to be 0. So now the x component of F3, so the x component of F3 is, well, if we knew what the magnitude of F3 was, and we knew what this theta was, then calculating the x component of F3 would be fairly easy. Its length would just be the length of this adjacent side of this right-angled triangle. So here it is. Now we don't know what those two quantities are yet, but there are two things that we want to figure out. So I think having them in here would be pretty handy. So we could then write an expression down for this F3x. An expression for that F3x would just be the length of this vector here, its magnitude. So we're going to have F3. And because this side of the right-angled triangle is the adjacent side, we need to multiply that by cos of theta. And because F3 is pointing in the positive x direction, then its x component comes with a positive plus sign. Now the y component of F3 is going to be the same thing, except that the length of its y component is just going to be the length of this opposite side over here. So the y component then is going to be F3 times sine of theta with a minus sign out the front because F3 is pointing in the negative y direction. And now we want to add these components up. We're going to have that the net force in the x direction is going to be the x component of F1 plus the x component of F2 plus the x component of F3. And if we just substitute in these expressions for these quantities, we find that, well, that's going to be 0 minus F2 plus F3 cos theta. Is all equal to 0. And I suppose if we wanted to, we might as well. Let's do a bit of rearrangement on this to make it look a little bit nicer. If we just add F2 to both sides of this equation, then we're going to have F2 minus F2 over here, and over here we're going to have 0 plus F2. So just adding F2 to both sides of the equation gets us to F2 is going to be equal to F3 cos of theta. And that looks like a fairly useful sort of equation. because it relates two things that we don't know to something that we do. So let me call that equation 1. Now we can get another one of these equations by adding up the forces in the y direction. So we're going to have that F net in the y direction then is going to be equal to the y component of 1 plus the y component of 2 plus the y component of 3. And they've all got to add up to 0. And if we just plug in these expressions for these components, we get this has got to be equal to F1. F2y is 0, so we get 0 there. And F3y is minus F3 sine theta. And that's all equal to 0. And just as we did up here, well, I guess we could just add F3 sine theta to both sides of this equation. And if we did that, what we'd come up with is that F1 is equal to F3 sine theta. And here we have another equation involving two things we don't know and one thing that we do. So let me call that equation 2. So what we have here is we have two equations, both involving two unknowns. So one thing we could do is if we take this expression here, if we take this equation and we solve it for F3, we could then take that F3 and plug it into equation 2, which would kill off this F3 and write it in terms of theta. If we did that, then this equation down here would only have one unknown in it. The only unknown in it would be this theta. And when we have one equation in one unknown, we're pretty much set. All we have to do is a little bit of algebra and we can figure out what that one unknown is. So let's do that. Let's solve equation 1 for theta. So we can say from equation 1, we know that to figure out what F3 is, we can just divide both sides by cos of theta. So in that case, we're going to have that F3 is equal to this F2 divided by cos theta. And now let's take this and plug it into equation 2. So we can now say plug into equation 2. And what we get then is we find that F1 is equal to F3, which is the same thing as F2 divided by cos theta, multiplied by this sine theta. And this is exactly the same thing as F2 multiplied by sine theta divided by cos theta. Now if we have a look on the formula sheet, or indeed at the back of the textbook, one of the things that we'll come across is the fact that sine theta divided by cos theta is equal to tan theta, which is very handy in this case because that will allow us to write these two trig functions in terms of 1. So instead of having two thetas, we'll have only one theta. And once we've got ourselves just one theta, we should be able to solve then for theta. So we know what F1 and F2 is, so we could just take these two numbers, plug them in here and figure out what the angle is, to figure out what direction F3 is pointing in. Once we've got that, we can take that angle and plug it back up into this equation here. So we just take F2, that 60, and divide it by cos of this angle.